नमस्कार, मैं हूं डॉक्टर राजकुमार जांगड़ा और आज हम लीनियर अलजेब्रा स्टार्ट करेंगे। लीनियर अलजेब्रा में सबसे पहले अपने पास आता है वेक्टर स्पेसेस एंड सबस्पेसेस। इंटरनल बाइनरी ऑपरेशन। In capital V, U star V belongs to capital V. For all U and V belongs to V, then star is internal binary operation. External binary operation. For each U belongs to V and A belongs to F, A star U belongs to capital V, then star is an external binary operation. नेक्स्ट आता है अपने पास वेक्टर स्पेस। वेक्टर स्पेस V is non-empty set of vectors and F is field of scalars. Then V is said to be vector space together with two binary operations. First, U plus V belongs to V for all U and V belongs to V. This is vector addition. Second, AU belongs to capital V for all A belongs to F and U belongs to V. This is scalar multiplication. V is said to be vector space together with two binary operations if first V plus this is an abelian group, that is V plus satisfies 5 properties. Second, properties of scalar multiplication. Properties of scalar multiplication. First is A into U plus V. This is equal to AU plus AV for all A belongs to F and U and V belongs to capital V. Second is A plus B into U. This is equal to AU plus BU for all A and B belongs to F and U belongs to V. Third one is A into BU. This is equal to AB into U for all A and B belongs to F and U belongs to capital V. And fourth is 1 into U is equal to U for all U belongs to V and 1 belongs to F. Then we say that V is a vector space. We can write it as V is a vector space over the field of scalar F. Next is vectors in Rn. Vectors in Rn. If u belongs to R, then u is a real number. If u belongs to R square, then u is of type xy, where x and y are real numbers. This is ordered pair. If u belongs to R cube, then u can be written as x, y, z, where x, y, z are real numbers. Up to so on like this. If u belongs to R raised to power n, then u is of the form x1, x2 up to xn. These are vectors in Rn. Now we prove some examples of a vector space. First example is if V is equal to R plus. R plus is this is set of positive real numbers, and capital F is equal to R. This is field of scalars, and two binary operation vector addition is defined as u plus v is equal to u into v for all u and v belongs to R plus, and a into u is defined as u raised to power a for all a belongs to f and u belongs to R plus. By these two properties, v is equal to R plus, this is a vector space. We can easily prove this. First, closure property. Closure with respect to addition. U and V belongs to R plus, that is U and V are positive real numbers. Then U into V also belongs to R plus, that is U plus V belongs to R plus. So addition is closed. Addition is closed. Next one is associative. U and V and W belongs to R plus, then U plus V plus W, this can be written as U plus V into W, this is U into VW, because multiplication is associative over real, so we can write u into vw as uv into w. This can be written as u plus v into w, and this is equal to u plus v plus w. Hence addition is associative. Third one is existence of an identity element. For all u belongs to R plus, 1 belongs to R plus such that u plus 1, this is equal to u into 1 is equal to u, and 1 plus u is equal to 1 into u, this is equal to u. So identity exists. Next is fourth property is existence of inverse. For each u belongs to R plus, there exists unique 1 by u belongs to R plus such that u plus 1 by u, this is equal to u into 1 by u, this is equal to identity. This u cancels u. Therefore, inverse exists. And fifth is commutative. Commutative. U plus v is equal to u into v, and this is v into u. This is equal to v plus u. So addition is commutative. Hence v plus this is an abelian group. Now properties of scalar multiplication. First property is a into u plus v. This is equal to a into uv. This is equal to uv raised to power a. This is equal to u raised to power a into v raised to power a, and this can be written as u raised to power a plus v raised to power a. This is equal to au plus ab. First property satisfied. Next is a plus b into u. This is equal to u raised to power a plus b, and this can be written as u raised to power a into u raised to power b. This is equal to u raised to power a plus u raised to power b, and this is also equal to au plus au plus b. And third property is a into bu. This is equal to bu raised to power a. This is equal to u raised to power b raised to power a. This is equal to u raised to power ba, and this can be written as u raised to power ab and ab into u. Hence this is third one. And 1 into u is equal to u raised to power 1. This is equal to u. Therefore, all four properties of scalar multiplication also satisfied. Hence, V is equal to R plus, with respect to two spatial boundary operation defined above, is a vector space. This is a vector space. Next example is, if V is equal to x1, x2, x3 and x4, where x1 first particular element is equal to 0 and xi's are real numbers, then this V is a vector space. With respect to simple binary operations, V first element is 0, therefore V plus, this is an abelian group, and four properties of scalar multiplication also satisfied, therefore this is a vector space. Next one, V is of the form x1, x2, x3, x4, where x1 is less than 0 and xi's are real numbers. So this is vector space or not. तो ये चेक करने के लिए हम एक u ले लेते हैं. Let u belongs to be any particular element where u is equal to -1, 2, 3, 4 and a is -1. Therefore, au is equal to 1, -2, -3 and -4. This doesn't belongs to V because जो first element is 1. This is not less than 0. Hence, this V is not a vector space. Next example is, if V is of the form x1, x2, x3, x4, where x1 is greater than 0 and xi's are real number. Similarly, we can prove that this is also not a vector space. And next example is, V x1, x2, x3, x4, where x3 square, this is greater than or equal to 0, and xi's are real number, then V is a vector space, because we know that square of any real number is always greater than or equal to 0. So this satisfies all the properties of a vector space, hence V is a vector space. If particular element is 0, that is first element is 0, second element 0, third 0, or fourth 0, then this is also a vector space. If particular element is non-zero, for example, V is equal to 1, x2, x3, x4, where xi's are real number, then this is not a vector space, because if we take u is equal to 1, 2, 3, 4, and v is equal to 1, 4, 2, 3, then u plus v is equal to 2, 6, 5, and 7. First element is not equal to 1. Therefore, u plus v, this doesn't belong to v. Hence, v is not a vector space. If v is of the form x1, x2, x3, and x4, where x3, x1 plus 4x2, this is equal to 0. This is a particular linear combination. In case of linear combination, there is no problem. This follow all the properties of vector space, hence this is a vector space. Now we come to next, subspaces. Subspace. Subspace. Let W be non-empty subset of a vector space V. Then this W is said to be a subspace of V if W is itself a vector space with respect to same binary operation defined in V. Hence W is a subspace. Therefore W सबस्पेस प्रूव करने के लिए हमें सेम 9 प्रॉपर्टीज सेटिस्फाई करनी है. W सबस्पेस कब होगा? जब वो सेम बाइनरी ऑपरेशन से इटसेल्फ क्या है वो एक वेक्टर स्पेस. दैट इज 5 प्रॉपर्टीज ऑफ वेक्टर एडिशन एंड 4 प्रॉपर्टीज ऑफ स्केलर मल्टीप्लिकेशन. देन दिस W इज ए सबस्पेस. अब आगे 9 प्रॉपर्टीज की बजाय हम आगे कुछ रिजल्ट्स का यूज करेंगे, जिससे हम 9 प्रॉपर्टीज प्रूव करने की बजाय कुछ प्रॉपर्टीज सेटिस्फाई कर देंगे. फर्स्ट, इफ W इज नॉन एम्प्टी सबसेट ऑफ V and first one is U plus V belongs to W for all U and V belongs to W, and second, AU belongs to W for all A belongs to F and U belongs to W, then W is a subspace. यहाँ हमें ये 9 प्रॉपर्टी सेटिस्फाई करने की जरूरत नहीं है, ओनली 2 प्रॉपर्टीज. सेकंड रिजल्ट इज if W is non-empty subset of V. First one is U minus V belongs to W for all U and V belongs to W. Second is AU belongs to W for all A belongs to F and U belongs to W. Then W is also a subspace. Next, third property. Third, if AU plus BV belongs to W for all A and B belongs to F and U and V belongs to W, then W is a subspace. Only single condition satisfies W is a subspace or not. Again, next, if we prove AU plus V belongs to W for all A belongs to F and U and V belongs to W, then W is also a सबस्पेस। तो सबस्पेस प्रूव करने के लिए हमारे पास ये 4 थ्योरम्स हैं। 4 रिजल्ट्स का हम यूज कर सकते हैं कहीं भी आगे जब हम एग्जांपल्स करेंगे उसमें फर्स्ट इनटू प्रॉपर्टीज का यूज करें या इनटू प्रॉपर्टीज का, या थर्ड रिजल्ट ओनली सिंगल कंडीशन, फोर्थ इज आल्सो सिंगल कंडीशन। इन 4 प्रॉपर्टीज का यूज करके 4 में से कोई भी एक रिजल्ट का यूज करेंगे, एनी वन रिजल्ट कैन प्रूव दिस इज ए सबस्पेस। Next, we prove important theorem, the intersection of two subspaces theorem. Let W1 and W2 be two subspaces of a vector space VF. Then prove that W1 intersection W2, this is also a subspace. Proof of theorem. Here W1 and W2 are subspaces. Therefore, 0 belongs to W1 and 0 belongs to W2. Hence, 0 belongs to W1 intersection W2. This implies W1 intersection W2 non-empty set. Again, W1 and W2 are subspaces of VF. Therefore, W1 subset of V and W2 is a subset of V. This implies W1 intersection W2 is a subset of V. Therefore, W1 intersection W2 is a non-empty subset of a vector space V. Now we prove that this intersection is a subspace. For this, let U and V belongs to W1 intersection W2 and A and V belongs to F. This implies UV belongs to W1 and UV belongs to W2 and A and B belongs to F. Because W1 and W2, these are two subspaces, therefore AU plus BV belongs to W1 and AU plus BV belongs to W2. This implies AU plus BV belongs to W1 intersection W2. Hence, W1 intersection W2 is a non-empty subset of a vector space V. This satisfies condition AU plus BV belongs to W1 intersection W2. Hence, W1 intersection W2 is a subspace of a vector space V. Therefore, intersection of two subspaces is again a subspace. Similarly, we can prove that arbitrary intersection of any family of subspaces of a vector space is again a subspace. But in case of union, in case of union, that is W1 union W2, result need not be true. For this, we have some example. First contradictory example, let W1 is equal to x0 0, where x is any real number and W2, this is 0, Y, 0, where Y belongs to R. W1 and W2 are two subspaces of a vector space, this XYZ, where XYZ are real numbers. Then W1 union W2, this is a set W where either W is equal to X0, 0 or W is equal to 0, Y, 0, where X and Y are real numbers. Here we prove this union is not a subspace. Let 1 0 0 0 1 0, this belongs to W1 union W2. Then 1 0 0 plus 0 1 0, this is equal to 1 1 0, doesn't belongs to W1 union W2. Hence W1 union W2 is not a subspace. So in case of union, need not be a subspace. Now we have some examples of subspaces. We prove some examples of subspaces. First example is, let V is equal to R cube. R cube, that is XYZ, where XYZ belongs to R, and W is XYZ, where 3x plus y minus z, this is equal to 0, and x, y, z are real numbers. Check this W is a subspace or no. For this, let U is equal to x1, y1, z1, and V is equal to x2, y2, and z2. This belongs to capital W. Then 3x1 plus y1 minus z1, this is equal to 0. Similarly, 3x2 plus y2 minus z2 is equal to 0. We prove that AU plus BV belongs to W. AU plus BV, this is equal to A into U, x1, y1, z1 plus B into x2, y2, z2. This is equal to ax1 plus bx2, ay1 plus में by2, az1 plus bz2. Au plus bv belongs to W if 3 time of first element plus 1 time of second element minus 1 time of third element must be equal to 0. We check this condition. 3 time of first element ax1 plus bx2 plus 1 time of second element minus 1 time of this element. This is equal to 3ax1 plus ay1 minus kaz1 plus 3bx2 plus by2 minus bz2. Taking common a, 3x1 plus y1 minus z1 plus taking common b, 3x2 plus y2 minus z2. This equal to 0, this equal to 0. Therefore, this must be equal to 0. Hence, AU plus PV, this belongs to W. Therefore, W is a subspace. W is a subspace. Next, we have another example. If W is equal to x1, x2, x3 where x1 plus x2 is greater than or equal to 0 where xi's are real number. Check this W is a subspace or not. Let u is equal to 1, 2, 3. Here 1 plus 2 is greater than 0. So u belongs to W. If we take a is equal to minus 1, then au is equal to minus 1 into 1, 2, 3. This is equal to minus 1, minus 2 and minus 3. And sum of first two elements is equal to minus 3. This is not greater than or equal to 0. So AU doesn't belongs to W. Hence, this is not a subspace. Next, we have another example. If W is equal to x1, x2, x3, where x1 into x2 is equal to 0 and xi's are real number, then check this is a subspace or not. For this, let u is equal to 1, 0, 0 and v is equal to 0, 1, 0. These elements belongs to capital W because product of first two element is equal to 0. If we take u plus v 1, 0, 0 plus 0, 1, 0, this is equal to 1, 1, 0. This doesn't belongs to W because product of first two element not equal to 0. Hence W is not a subspace. Next we have another example. Let W is equal to x, y, z where x, y, z are belongs to Q, where Q is set of rational numbers. Check this is a subspace or not. Over the field of scalars F, this is set of real numbers. If we take u is equal to 1, 2, 3 and a is equal to root 2, then au is equal to root 2 into 1, 2, 3. This is equal to root 2, 2 root 2 and 3 root 2. This doesn't belong to W because root 2 is not a rational number, hence this is not a subspace. Next example is let V set of all real valued functions and W is set of all even functions, that is W is collection of function where f of minus is equal to f of x. So check this is a subspace or not. Let f and g belongs to W. Therefore f of minus x is equal to f of x and g of minus x, this is also g of x. Then we check f plus g of minus x, this is f of minus x plus g of minus x, this is equal to f of x plus g of x, this must be equal to f plus g of x. Therefore f plus g belongs to W. Second is af of minus x, this is equal to a into f of minus x, this is a into f of x, this can be written as af of x. Hence AF belongs to W, therefore W is a subspace. Next one is if W is set of all continuous functions functions, we know that sum of two continuous functions is again a continuous function. Therefore, if f and g belongs to W, this implies f plus g also belongs to. If f is continuous function, if f belongs to W and a is any scalar, therefore af is also continuous function. So af belongs to W, hence W is a subspace. Next is, if V is set of all V is set of all n square matrices over reals and W set of all lower triangular matrices, then W is also a subspace, because we know that sum of two lower triangular matrices is again a lower triangular matrix. Also, scalar multiplication with a lower triangular matrix is again a lower triangular matrix. So this W is also a subspace. Similarly, we can prove that if W is collection of all scalar matrices, then sum of two scalar matrices is again a scalar matrix, and multiplication with a scalar matrix is again a scalar matrix. Also, sum of collection of all symmetric matrices is also a subspace, because we know that sum of two symmetric matrices is again symmetric matrix, and scalar multiplication with a symmetric matrix is again a symmetric matrix. But in case of singular matrices, for example, if W is equal to matrix A where determinant of A equal to 0, this is not a subspace. For example, let A is equal to 1 0 0 0 and B is equal to 0 0 0 1. A and B belongs to W, but A plus B is equal to, this is 1 0 0 plus 0 0 0 1. This is equal to 1 0 0 1. This doesn't belong to W because this is a non-singular matrix. Hence, this W is not a subspace. Similarly, we can prove that if W is equal to A, where A is n cross n order matrix and determinant of A not equal to 0, this is also not a subspace. If W is collection of all diagonal matrices, then this is a subspace. Next we have linear sum.